Assalamu alaikum students. In today's lecture, you will learn about the Charles law, the derivation of the absolute temperature, derivation of the general gas equation involving Boyle's law, Charles law, and Avogadro's law, and the values of R will also be discussed along with that of the examples. Now, this is Charles law, which explains the effect of change in temperature on the volume of the gas. The introduction about it is it was given by the Jacques Charles, who derived the relationship between the volume of the gas and the temperature in 1787, and it is termed as Charles law. What the statement is, the general statement is the volume of the given mass of that gas is directly proportional to the absolute temperature when the pressure and the number of moles is kept constant, right? Now the means the volume and the temperature, they are related, what you say, directly. As the temperature will increase, volume will also increase. As the temperature will decrease, volume will also decrease. It is a general one statement given by Charles law. What about its critical definition? If you remember, I have told you earlier when we learned about that of the absolute scale of temperature, that is the Kelvin scale. Here it is given. It is stated that at constant pressure, the volume of the given mass of the gas increases or decreases by the factor of 1 upon 273 times of its original volume at 0 degree centigrade for every 1 degree centigrade rise or fall in the temperature respectively. Right, so here we have to consider the fraction, that is 1 upon 273, which will be added to that of the, what you say, whatever the temperature being increased or decreased for every rise or fall of the temperature with the increase or decrease in the volume. Now here we have the different. Now here it is given the experimental verification of the law, that is Charles law. Here it is given the, suppose this is the initial one, temperature, pressure, and volume terms. While in this container, when you have heated it or maybe you have cooled it, this time it is when you have heated it, this is going to give you the final state of volume and temperature, while the pressure is kept constant. You can see on both the containers the pressure applied is same, that is 1 atmosphere. It is supplied with a movable piston. Inside it, there is, in the first one container, there is the volume that is occupied by the gas inside, that is 0.5 liters at 200 kelvins, right? But when you are going to heat it, what happens? The volume inside becomes double as the temperature became double, right? You can see the volume rises from 0.5 liters to 1 liter, while temperature rise is from 200 to 400. It's a double, so that we say there is a linear relationship between volume and temperature. As you will double the volume, as you will increase the temperature, the volume will also be increased in the same ratio, right? So the must conditions are there. Number of particles should remain same inside the container, as well as the atmospheric pressure or the external pressure should also remain same. Initially, if we say that, what you say, the law says that V is proportional to T, and if I replace this, the proportionality sign, you will get there V is equal to KT. We can also write it as V upon T, that is equal to K, right? Suppose you have applied it for the initial conditions, so you will get there V1 over T1, and if you are applying it for the final condition, so it will be V2 upon T2. Both of them are the values of K, so you can write it as V1 over T1 is equal to V2 upon T2. This is the second form of this law, which is applied mostly in the numericals, right? Now come to the next one. Here we have the verification of this law by an illustration or IGF given here. You can see here the inside container, there is present the gas particles. Outside pressure is constant, that is the 1 atmosphere. Here you can see pressure is 1.50 atmosphere, while the temperature is going to rise as we are going to heat it from 250 to 450 degrees centigrade. Here on the other side, there is given a graph between volume at the y-axis and temperature at the x-axis. The linear relationship occurred between the two parameters, right? So whatever the temperature is rising, the volume will rise in the same manner, right? When we are going to double the temperature, the volume will also be doubled. This is what we say is the Joul's law. Now, as I told you earlier, there is a critical form of the Joul's law as well, which is stated as at constant pressure, the volume of the given mass of a gas increases or decreases by a factor of 1 upon 273 times it is increased from its original volume at 0 degree centigrade for every 1 degree centigrade rise or fall in temperature respectively. The preliminary observations which were done by the Charles, he observed that the gases which are, that is the hydrogen one or carbon dioxide or oxygen gases, they expand equally on heating from 0 degree centigrade to 80 degrees centigrade, means their behavior is same, right? So how this behavior is being calculated, for which we have to derive the critical form of the law. Here it is given, the volume of the gas at 0 degree centigrade is equal to V naught, that is the original volume of the gas at 0 degree centigrade is represented by V naught. Now we want to calculate what will happen that the gas temperature is increased from 0 degree centigrade to 1 degree centigrade. Now what will be the volume of the gas by 1 degree centigrade rise in the temperature, right? For which we have to write it like this. In between these to just leave it, इनको नहीं लिखें, ये जो है प्रेजेंट किए हुए हैं. Otherwise अगर लिखना है तो it will be written as V1 naught, V2 naught and VT naught, right? Now here we have to write it as at 1 degree centigrade the volume will be V naught plus, as the it is increasing in the from in the original volume there is an increase by the factor of 271 upon 273. So here the original volume at 0 degree centigrade plus there is addition of this factor, that is increase in its original volume by the factor of 1 upon 273, right? This 1 represents you the 1 degree rise in temperature, right? Now if we want to get it by the rise of the 2 degree centigrade, then you can write it like this. This is the original volume at 0 degree centigrade plus increase in this original volume by the factor of 2 upon 273 now, because there is 2 degree rise in the temperature. So it will be written as 2 upon 273. Similarly, if you want to get the volume at T degree centigrades, so you have to write it as V naught original volume plus increase in its original volume, that is by T upon 273, right? Now here you can write it like this, V volume at the temperature T, T can be any temperature, right? Now is equal to, if we want to take it out as a common factor, V naught from this equation, right? So you can write it like this, V naught in the bracket there will be 1 plus T upon 273. By taking out LCM you will get there 273 plus T upon 273. Now here this one gives you the Kelvin temperature. If you have learned it in the previous one lecture, that T, that is the temperature in degree centigrades, plus 273 will give rise you the temperature in Kelvin scale, right? So you can write it as V at the temperature T is equal to the original volume and having the in the bracket that is T upon 273, right? Or you can write it like this, that Vt is equal to V naught upon 273 T. So for every 1 degree rise, there will be increase in the volume by means of the factor of 273. You can put up the value and you can calculate it. For example, here you can calculate the volume, that is 273 plus, if you want to get it at 1 degree centigrade, so it will become 1 upon 273 in this equation, and 273 plus 1 upon 273. So it will give you the volume at the 1 degree rise. Okay, now come to that of the next one. Now here it is given the graphical presentation of Charles law. It is an isobar type graph in which you can see the relationship between volume on y-axis and temperature on x-axis every time a straight line is produced whenever we have changed the pressure. Means once you have selected a pressure, then you have performed experimentation by changing the temperature with respect to that of the which, with respect to which the volume has also been changed. So when you draw the values, you will get a straight line at a fixed one pressure, right? Then we have done another experimentation by the changing of the external pressure. Then throughout the experimentation, that pressure will be kept constant and the different values of temperature and volume will be produced, right? Similarly, we have changed the external pressure once again, that is P3. Again, during experimentation, you have kept the pressure constant, and now what the values you get about that of temperature and volume, again it is given in the form and of a straight line. You can see every time we are getting a straight line, whatever the pressure you have selected, right, which shows that there is a relationship between that of the temperature and volume, right, which will be observed at every one pressure, right? Although there is decrease in the volume inside the container when you are increasing external pressure, right? So that's why each next one bar is moving down there. You can see here the P4 is lying near to that of the x-axis. It is ultimately moving downwards, right? So when we have the low pressure, the volume will be high, and when we have the high pressure, volume will be low. After what you say, you have selected the pressure, then you will observe the changes of temperature and volume, right? Now this is what we say Charles law, that the V is proportional to T. Okay, now here it is given the derivation of the absolute zero. What is absolute zero and why it is called so? It is the lowest possible temperature on earth at which we say that the every motion ceases, the volume of the gases becomes zero. How it is being calculated? You have done the critical form of the Charles law, according to which we say the volume of at any of the degree centigrade, it can be calculated in Kelvin scale like this, that it gives you the V naught plus the factor of 1 upon 273 may be increased or decreased from the original volume, right? So that you can calculate the volume of the gas at a particular temperature. Maybe there is increase in temperature, maybe there is decrease in temperature. Now this one equation is with respect to increase in temperature, that is 1 degree rise took place. Okay, now here if the gas is occupying the 0 degree centigrade, then you are further decreasing the temperature. Now how this term will change? This term will change like this, that V volume at -1 degree centigrade is equal to, suppose you are writing with decrease in 1 degree temperature, okay? So what will you write here? It will be 1 degree decrease आपके पास में जा रहा है. So how you can turn this equation? It will be like this: V naught minus V nauट ओरिजिनल वॉल्यूम में से यही फैक्टर आप सब्ट्रैक्ट कर देंगे. This value, this equation actually will give you the value of the volume at -1 degree centigrade. minus 1 degree centigrade. Similarly, if you want to calculate the volume of the gas at minus 273 degrees centigrades, it will transform like this: V naught minus V naught 273 upon 273. If we calculate it by taking the V naught common, so it will give you the value of 0. Means the volume becomes negligible or 0 when the temperature is decreased up to 273 degrees, minus 273 degrees. Right? So this is termed as this temperature at which the volume becomes 0. It is called absolute 0. Look at the graph. You can see here a graph is plotted between volume on y-axis and temperature at x-axis. Now you can see the drop in temperature is intersecting the volume line at 0 degree centigrade, and then further an extra plotting is done with the broken line, and it touches the temperature with the 0 volume at minus 273 degrees centigrade. What does it explains? It means that from the higher temperature, when you are moving towards that of the lower temperature, up and until it intersects the volume line at 0 degrees centigrade, the gas is existing as a gas, right? But then when you have decreased for the temperature further, the gases, unless they go to that of the 0 volume, instead of it, it changes its physical state, right? It changes its physical state. Maybe it will be converted into that of the liquid, or maybe it's converted into solid, because the volume can never be 0. But we are considering an ideal gas. An ideal gas is that gas which obeys the gas laws, right? So this extra plotting shows that this is the temperature of minus 273 degrees at which the volume of the gas will become 0. But unfortunately, before we reach this temperature, every gas, it changes from gaseous state to that of the other states, maybe liquid or the gases. Means no such gas, ideal gas exists which have the absolute 0 temperature at which its volume will become 0. But before reaching this temperature, it will be turned to liquid or the solid state, right? So this is what we say, this before we go to that of the temperature minus 273 degrees, the gases will liquefy or will turn to the solids. So this is considered as the lowest possible temperature, and it is called absolute 0. Now come to the next one. What is the significance of this absolute 0? This tells you that it is not possible to have a gas at absolute 0 because it changes into liquid or solid states, as I told you now. At minus 273.15 degrees centigrade, the gas particles do not move and the volume of the gas becomes minimum, that reaches to 0 according to the graph it is being given. The absolute 0 may be initialized to get the Kelvin scale of temperature. Yes, you can find out the temperature in the Kelvin scale. Now the 0 Kelvin minus 273.16 degrees centigrade is called as the absolute 0, which is the lowest possible temperature, as I told you earlier. Now, there's an example mentioned with respect to the form of that of the Charles law. Here it shows that 50 centimeter cube of gas in a syringe at 15 degrees centigrade is heated to 50 degrees centigrade, and the piston of the syringe is allowed to move outwards against the constant atmospheric pressure. Calculate the new volume of the hot gas. Here you can see 50 centimeter cube tells you the volume which was present initially. So it is the value of V1. Temperature mentioned is 15 degrees centigrade. It is the initial temperature. Now you have increased the temperature up to 50 degrees centigrade. So it will be T2, and you have to find out V2 with the change of this temperature. right? So first of all, convert these temperatures into Kelvin, because otherwise you will not get a correct answer if you will make use of the degree centigrades. All the questions of this gas laws chapter, that will be done by means of the conversion of the degree centigrade temperature into the Kelvin temperature. Otherwise, calculations will be wrong, right? The formula which will be applied is the second form of the law, that V1 over T1 is equal to V2 upon T2. You have the values of V1, T1 and T2. So take it out, rearrange the equation in such a way that you can get the value of V2, right? So the answer is being mentioned. It is 56 centimeter cubes. Another self check is being given in your book. You can see here. Before this, there is an example mentioned that at 17 degrees centigrade, a sample of hydrogen gas occupies 125 centimeter cube. What will be the volume at 100 degrees centigrade? The similar type of the what you say numerical as we have done in this slide. That is the 17 degrees centigrade, the initial temperature. The volume is 125 centimeter cubes. Then you have the second temperature of 100 degrees centigrade. You have to calculate the V2. Do it yourself, find it out what is your answer, right? Now as self check is being mentioned, we will do it in the next one, what you say, in the next one lecture. Come to the next one. Here we have the Avogadro's law. Avogadro's law tells you the relationship between that of the number of moles and that of the volume of the gas particles, right? It says that at constant temperature and pressure, remember it, both the terms are being kept constant, that is temperature and pressure, the volume of a gas is directly related to the number of moles. Means it depends upon the number of moles. It was given by Amedeo Avogadro, so it is represented by V proportional to N when temperature and pressure is kept constant. If you rearrange it, you will get there V is equal to Kn. For the initial and final state, it will be V1 upon N1 is equal to V2 upon N2. It is presented by this experimental diagram. You can see outside pressure is every time 1 atmosphere. When we move from the initial state, this is initial state and this is the final state. When we are going to move from initial to final, 1 mole of the substance is occupying the volume 22.4 liters. If you have increased the number of moles, there will be increase in the volume, right? So this is, we say, if you are going to add up the gas molecules or if you are going to remove the gas molecules, there will be ultimate effect on the volume of the gas within this container, right? Now here we have the next one. You can see Avogadro's law and the relationship with that of the quantities of the, or you say the molar volumes of the substances. It is being mentioned here that the 0.09 gram of hydrogen at STP is equal to 1 dm cube, right? 0.09 grams. But what about 2.016 grams of hydrogen at STP? STP stands for standard temperature and pressure, right? So you want to calculate at 2.106. So it will be 1 upon 0.09 into 2.106 is equal to 22.414 dm cube. It is, as you can see, hydrogen gas is present in the form of a molecule. So it is considered as the mole. It is 1 mole of the substance which is having mass 2.016 grams. Right, so 1 mole of hydrogen at STP will occupy the volume 22.414 dm cube. This is termed as the molar volume. Here it is being given the equal volumes of all gases at same temperatures and pressures. They contain equal number of molecules. All the gases, for example, here you can see 3 gases are being present in these 3 balloons. You can see helium, nitrogen and methane. What about their volume? About their what to say masses? Helium carries mass how much? 4 grams. Nitrogen carries 28 grams. Methane carries 16 grams. There is a difference in their mass, but remember them, they all are a single unit, right? So the pressure kept same, that is 1 atmosphere. Temperature kept same, that is 0 degrees centigrade. What about their volume? They all are the 1 mole, having same temperature, having same pressure. So the volume occupied will also be same. That is because you are considering 1 mole of the substance, and each 1 mole carries the number of particles in it, that is 6.02 10 to the power 23 particles. So each one gas is having the volume 22.4 liters. Right? Now here it is given ideal gas equation for the derivation. You can be asked a question, derive ideal gas equation and find out various values of R, right? So then you have to do this one. The question is, what is meant by ideal gas? As I told you earlier, that the gas which obeys all the gas laws at all temperatures and pressure, especially the laws which are concerned, they are Boyle's law, Chau's law, and Avogadro's law. So they are considered as ideal gases, right? So this equation shows you the effect of the simultaneous changes in pressure and temperature on the volume of the given gas, that is termed as the ideal gas equation. The 3 laws considered are Boyle's law, Chau's law, Avogadro's law, and then we have the derivation. You know what are the relationship between these all. Volume is proportional to 1 upon P. Volume is proportional to T according to Chau's law, and according to Avogadro's law, volume is proportional to N, that is number of moles. All these are the values of V, right? So V is proportional to N T upon P. If we replace the proportionality sign, so you will get there V is equal to nRT upon P. And if I turn this P on the other side, you will get there PV is equal to nRT. This is called general gas equation, right? This is called general gas equation, and R is termed as the general gas constant, which is having specific value at STP and SI units, right? Now here we have, if you are going to apply it for the initial state of a gas and the final state of a gas, then how to get it? You will find there for the initial, you will get there P1 V1 is equal to N1 R T1. Remember, R will stay constant. You are taking it out as the value of R, so it will turn like this. क्या रह जाएगा पीछे? PV upon NT. PV upon NT. Right? So it will be P1 V1 over N1 T1. Now consider you are having the number of moles that is equal to 1. So you can skip the N now here, right? So the equation turns like PV upon T, that is equal to R. For initial state, it will be P1 V1 over T1, and for the final state, it will be the P2 V2 over T2. Both are the values of R. Now compare them like this. This one, P1 V1 over T1 is equal to P2 V2 over T2. This is called the second form of this ideal gas equation, right? It is quite simple and easy, you can learn it. Now here it is explaining you the ideal gas equation, which gives you the effect of change in temperature and pressure on the volume of a gas. With respect to that of an example, it is being explained here that all the gas volumes, they are usually compared at 0 degree centigrade in the terms of Kelvin and 1 atmosphere. These are the units of the temperature and pressure which will be used in STP, right? By using this one, we have to solve this example number 10. Look at this carefully. A certain mass of gas occupies 1000 centimeter cubes at 57 degrees centigrade and 723 millimeters of Hg. Now you should know 1000 centimeter cubes tells you volume, 57 degrees centigrade tells you temperature, and 723 millimeters of Hg tells you what? It tells you about the pressure, right? He's asking you what will be the volume at STP, means the second value of temperature and pressure will be taken from the standard terms. That is 0 degree centigrade will be considered and the pressure will be considered as 1 atmosphere. You have to apply the equation P1 V1 over T1 is equal to P2 V2 over T2. So here you have to calculate the value of V2, right? So very carefully you have to transform this equation in such a way that V2 should come out from all these parameters and this equation get rearranged. Before this, what you have to do, you have to turn the temperature into Kelvin scale. Remember it, right? Put up the values, you will get your answer here. There is no need for the R as we have not applied it here, right? Now come to the next one. Now students, it is enough for today's lecture. Learn what have you listened in the lecture. Read it again and again and remember the values of the standard temperature and pressure and the formulas applied for the better understanding and use in the numerical, right? So till the next one lecture, Allah.